Hello everyone, I hope you're all enjoying the MonSec Beginner CTF. I'm Leo and I'm going to be giving a quick run through of two of the crypto challenges to help anyone that may be stuck, unsure of where to proceed or just what to look up. I'm intending for this not to be a complete walkthrough or set of solutions to the challenges, but hopefully you should know roughly where to proceed after watching this. Now the first challenge we're given is the challenge named Dr. Octopus, which is clearly named in reference to the Octa system which Monash has started using recently. Now the format of this challenge is quite similar to a typical crypto CTF challenge, where they give you a program that has been redacted to remove the flag but is otherwise identical, along with an IP address and port that we can connect to using Netcat. Now your IP address will be slightly different, obviously. Once we connect to it, it will run this program remotely, but the flag will be actually what you're looking for. And so let's have a look through this program here. Essentially, we want to get this line of code to execute, which prints the flag out. And just running it, if we enter our name, it will enter a challenge. So it's printing So it's printing a challenge, which is a random number between 0 and 200,000, and then checking to see if our input is equal to a randomly generated number between 0 and 200,000. Now, a 1 in 200,000 chance is quite low, and so I'm very certain that we're not going to guess the right number, and of course we won't. And so we need to find some way to exploit a weakness in this program to get the flag. Now, if you know anything about securely generating random numbers, one thing that may immediately jump out to you is this line here, random.seed username. Now, in case you're not aware, what it means to seed random is to essentially set a starting point or a starting set of conditions for a random number generator. Now, just for reference, let's say we import random in the same way that this challenge has. Now these numbers here are going to be quite unpredictable, clearly by design, because it's random. But if we were to seed it with a value that we know, so then we generate this, the first number will be this, the second will be this, third will be this, fourth will be this, and so on. And even if we quit this and do the same thing, and seed it with a value we know, the first number will still be this, even in a different session. The second number will still be this, the third number will still be this, and so on and so forth. And so basically, by knowing the starting position, or the starting set of parameters that are used in Python's random number generator, we can predict what the future numbers will be. And try to think about how this would be helpful in this challenge here. It is printing a challenge with a random number, and then asking you to see if your input is equal to the next random number. And so essentially, we need to figure out whereabouts in the chain of random numbers we are. Now, it's a bit more complicated than it seems, because the first thing this is doing, before the value has been seeded, it is setting the variable repeat times to be a random integer between 0 and 20. And we don't know what this is. And for that amount of times, between 0 and 20, it's generating a random number. So we are somewhere between 0 and 20 steps along in the chain already, and we need to figure out where we are roughly. And so let's just seed it with our name, which we've already provided here. So if we random.seed with our username Leo that we've already given, and then let's say we do this. And you might see the challenge here is 45246. And if we have a look around in here, hang on, if I miss 45246. Oh, I'm sorry, I just realised I shouldn't put the wrong amount of zeros in there. So 200,000 rather than 20,000. And we should get, yep, there we go, 45246. Now try to think, now I'm not going to reveal the challenge or reveal the solution exactly, but try to think about what it means or the significance of knowing roughly whereabouts in the chain of random numbers you are, and how important it is to know what the seed is. So given here we know what this value here is, try and think about how you can get this to work to predict the future numbers. Alright, now the next challenge I'm going to have a look at is an RSA challenge. Now, in this case, all we're given is, sorry, shouldn't have had that there, but all we're given is this set of numbers here. N is equal to this, C is equal to this, E is equal to that. Now, in case you haven't seen RSA before, RSA is what's called a public key cryptosystem, which means that it differs from traditional cryptography. In normal or symmetric cryptography, if you encrypt a message with a key, you have to use that key to decrypt it, which makes sense. But in public key cryptography, when you encrypt a message with a public key, and then you decrypt with a private key, which means that even if you know the key that the message was encrypted with, you still can't decrypt it without knowing the private key. Now, if you were to Google something, say, if you look up the RSA cryptosystem on Wikipedia, it's got some interesting stuff on key generation, which talks about how it works. But generally speaking, the way it works is the public key is a set of numbers E and N. Now, E is sometimes called the public exponents, and N is the modulus, and we've already got them here. And the private key is a set of numbers D and N. Now, we don't know D, because obviously we don't know the key for decryption straight off the bat, but N is the same. Now, the way it works is, to encrypt a message, now typically the message, or the plain text, M, typically the plain text is referred to as M. The way it works is, you get the message, raise it to the power of E, raise it to the power of 65,537 here, and then reduce it over a modulus of N. Now, a modulus is just a remainder after division. For example, 12 mod 10 would be 2, because there's a remainder of 2 after you... there's a remainder of 2 after 10. And then, once you're given the message, and so this is equal to C, the ciphertext, which is what we have here. But what we want to calculate in order to solve this is to say C to the power of D, which is the private key for decryption, mod N, is equal to M. Now, M is the plain text, which is often what we're after, and usually contains the flag. Now, once again, looking at some information about the RSA cryptosystem, we need to calculate D, because D is the only number we don't know. And to calculate D, you can look at here. You can see N is equal to the product of two prime numbers, P and Q, and the next thing that is done is they calculate a totient function. They calculate a totient function, which is equal to P minus 1 times Q minus 1, and then D is equal to the inverse multiplicative inverse of that, of E, over that modulus. So essentially, phi is equal to P minus 1 times Q minus 1, where P times Q equals N. Now, the reason that RSA is so secure is that finding the prime factors of a large number, being N, is often very difficult to do. And so they don't actually give you the values of P and Q, and so they expect you to find them in this challenge. So the way to do this is, the way you typically solve this is by finding the values of P and Q. P is equal to something, Q is equal to something, we don't know what they are, and then we already know E, and so D is equal to the inverse of E, phi is equal to P minus 1 times q minus 1. D is equal to the modular multiplicative inverse of E and phi. And now, as I mentioned earlier, c to the power of D mod n is equal to the message is what we're after. And so once we know D, we can find the message by saying m is equal to power. Now this function here is just a more efficient way that Python gives to calculate powers for you. M is equal to the power of c to the power of D mod n. And then if you print that number, you might see, just as a word of advice, when you do this challenge, try printing the number in hex, because once you see the number in hex, it might make more sense how you get the flag from it, because obviously the flag is going to be ASCII printable characters. And yeah, and you're probably thinking, how do you actually find these values of P and Q? Well, the most efficient way, and the first thing you should always check in an RSA challenge, is to look at FactorDB. And if you check here, FactorDB already has these factors for you. And so if you can chuck these numbers in here, if you can chuck both these numbers in here, you can calculate this. And there are plenty of libraries out there that can do the inverse function for you, such as crypto-util number. I think you import this by doing pip install pycrypto or pip install pycryptodome, and it will do this for you. Or it might be, actually, yeah, no, I believe that's what the function's called. Now, one thing that you might find is that in some challenges there might actually be more than one factor. This challenge isn't like that, but I believe that there is another challenge that's going to have more than 2 factors in it. And in that case, you can just keep on multiplying phi by those numbers minus 1. And if you do this right, you should be able to figure out the flag with these hints. Alright, I think that's about it. I hope you all have good luck in solving the rest of these challenges. I'll leave it here.